Disc 6.
Today, accelerators have names that sound like something Flash Gordon would use in battle. The Super Proton Synchrotron, the Large Electron Positron Collider, the Large Hadron Collider, the Relativistic Heavy Ion Collider. Using huge amounts of energy, some operate only at night, so that people in neighbouring towns don't have to witness their lights fading when the apparatus is fired up. They can whip particles into such a state of liveliness that a single electron can do 47,000 laps around a 4-mile tunnel in a second. Fears have been raised that in their enthusiasm scientists might inadvertently create a black hole or even something called strange quarks, which could theoretically interact with other subatomic particles and propagate uncontrollably. If you're reading this, that hasn't happened. Finding particles takes a certain amount of concentration. They are not just tiny and swift, but also often tantalizingly evanescent. Particles can come into being and be gone again in as little as 1/10⁻²4 of a second. Even the most sluggish of unstable particles hang around for no more than 1/10⁻⁷ of a second. Some particles are almost ludicrously slippery. Every second the Earth is visited by 10,000 trillion tiny, all but massless neutrinos, mostly shot out by the nuclear broilings of the Sun, and virtually all of them pass right through the planet and everything that is on it, including you and me, as if it weren't there. To trap just a few of them, scientists need tanks holding up to 12.5 million gallons of heavy water, that is, water with a relative abundance of deuterium in it, in underground chambers, old mines usually, where they can't be interfered with by other types of radiation. Very occasionally, a passing neutrino will bang into one of the atomic nuclei in the water and produce a little puff of energy. Scientists count the puffs, and by such means take us very slightly closer to understanding the fundamental properties of the universe. In 1998, Japanese observers reported that neutrinos do have mass, but not a great deal, about 1/10,000,000th that of an electron. What it really takes to find particles these days is money, and lots of it. There is a curious inverse relationship in modern physics between the tininess of the thing being sought and the scale of facilities required to do the searching. CERN, the European Organization for Nuclear Research, is like a little city. Straddling the border of France and Switzerland, it employs 3,000 people and occupies a site that is measured in square miles. CERN boasts a string of magnets that weigh more than the Eiffel Tower, and an underground tunnel over 16 miles around. Breaking up atoms, as James Trefil has noted, is easy. You do it each time you switch on a fluorescent light. Breaking up atomic nuclei, however, requires quite a lot of money and a generous supply of electricity. Getting down to the level of quarks, the particles that make up particles, requires still more. Trillions of volts of electricity and the budget of a small Central American nation. CERN's new Large Hadron Collider, scheduled to begin operations in 2005, will achieve 14 trillion volts of electricity and cost something over $1.5 billion to construct. There are practical side effects to all this costly effort. The World Wide Web is a CERN offshoot. It was invented by a CERN scientist, Tim Berners-Lee, in 1989. But these numbers are as nothing compared with what could have been achieved by, and spent upon, the vast and now unfortunately never-to-be superconducting Super Collider, which began being constructed near Waxahachie, Texas in the 1980s, before experiencing a super collision of its own with the United States Congress. The intention of the collider was to let scientists probe the ultimate nature of matter, as it is always put, by recreating as nearly as possible the conditions in the universe during its first 10,000 billionths of a second. The plan was to fling particles through a tunnel 52 miles long, achieving a truly staggering 99 trillion volts of energy. It was a grand scheme, but would also have cost $8 billion to build, a figure that eventually rose to $10 billion, and hundreds of millions of dollars a year to run. In perhaps the finest example in history of pouring money into a hole in the ground, Congress spent $2 billion on the project, then cancelled it in 1993 after 14 miles of tunnel had been dug. So Texas now boasts the most expensive hole in the universe. The site is, I'm told by my friend Jeff Gwynn of the Fort Worth Star-Telegram, essentially a vast cleared field dotted along the circumference by a series of disappointed small towns. Since the Super Collider debacle, particle physicists have set their sights a little lower, but even comparatively modest projects can be quite breathtakingly costly when compared with, well, almost anything. A proposed neutrino observatory at the old Homestake mine in Lead, South Dakota, would cost $500 million to build, this in a mine that is already dug, before you even look at the annual running costs. There would also be $281 million of general conversion costs. A particle accelerator at Fermilab in Illinois, meanwhile, cost $260 million merely to refit. Particle physics, in short, is a hugely expensive enterprise, but it is a productive one. Today the particle count is well over 150, with a further 100 or so suspected. But unfortunately, in the words of Richard Feynman, it is very difficult to understand the relationships of all these particles, and what nature wants them for, or what the connections are from one to another. Inevitably, each time we manage to unlock a box, we find that there is another locked box inside. Some people think there are particles called tachyons, which can travel faster than the speed of light. Others long to find gravitons, the seat of gravity. At what point we reach the irreducible bottom is not easy to say. Carl Sagan in Cosmos raised the possibility that if you travelled downward into an electron, you might find that it contained a universe of its own, recalling all those science fiction stories of the 50s. Within it, organized into the local equivalent of galaxies and smaller structures, are an immense number of other, much tinier elementary particles, which are themselves universes at the next level, and so on forever, an infinite downward regression, universes within universes, endlessly, and upward as well. For most of us, it is a world that surpasses understanding. To read even an elementary guide to particle physics nowadays, you must now find your way through lexical thickets such as this. The charged pion and antipion decay respectively into a muon, plus antineutrino, and an antimuon, plus neutrino, with an average lifetime of 2.603 times 10 to the minus 8 seconds. The neutral pion decays into 2 photons, with an average lifetime of about 0.8 times 10 to the minus 16 seconds, and the muon and antimuon decay respectively into... and so it runs on. And this from a book for the general reader by one of the normally most lucid of interpreters, Steven Weinberg. In the 1960s, in an attempt to bring just a little simplicity to matters, the Caltech physicist Murray Gell-Mann invented a new class of particles, essentially, in the words of Steven Weinberg, to restore some economy to the multitude of hadrons, a collective term used by physicists for protons, neutrons, and other particles governed by the strong nuclear force. Gell-Mann's theory was that all hadrons were made up of still smaller, even more fundamental particles. His colleague Richard Feynman wanted to call these new basic particles partons, as in Dolly, but was overruled. Instead, they became known as quarks. Gell-Mann took the name from a line in Finnegan's Wake, 3 quarks for Master Mark. Discriminating physicists rhyme the word with storks, not larks, even though the latter is almost certainly the pronunciation Joyce had in mind. The fundamental simplicity of quarks was not long-lived. As they became better understood, it was necessary to introduce subdivisions. Although quarks are much too small to have color or taste or any other physical characteristics we would recognize, they became clumped into 6 categories: up, down, strange, charm, top, and bottom, which physicists oddly refer to as their flavors, and these are further divided into the colors red, green, and blue. One suspects that it was not altogether coincidental that these terms were first applied in California during the age of psychedelia. Eventually, out of all this emerged what is called the Standard Model, which is essentially a sort of parts kit for the subatomic world. The standard model consists of 6 quarks, 6 leptons, 5 known bosons, and a postulated sixth, the Higgs boson, named for a Scottish scientist, Peter Higgs, plus 3 of the 4 physical forces, the strong and weak nuclear forces and electromagnetism. The arrangement essentially is that among the basic building blocks of matter are quarks. These are held together by particles called gluons, and together quarks and gluons form protons and neutrons, the stuff of the atom's nucleus. Leptons are the source of electrons and neutrinos. Quarks and leptons together are called fermions. Bosons, named for the Indian physicist S.N. Bose, are particles that produce and carry forces and include photons and gluons. The Higgs boson may or may not actually exist. It was invented simply as a way of endowing particles with mass. It is all, as you can see, just a little unwieldy, but it is the simplest model that can explain all that happens in the world of particles. Most particle physicists feel, as Leon Lederman remarked in the 1985 PBS documentary, that the standard model lacks elegance and simplicity. It is too complicated. It has too many arbitrary parameters, Lederman said. We don't really see the creator twiddling 20 knobs to set 20 parameters to create the universe as we know it. Physics is really nothing more than a search for ultimate simplicity. But so far all we have is a kind of elegant messiness, or as Lederman put it, there is a deep feeling that the picture is not beautiful. The standard model is not only ungainly, but incomplete. For one thing, it has nothing at all to say about gravity. Search through the standard model as you will, and you won't find anything to explain why, when you place a hat on a table, it doesn't float up to the ceiling. Nor, as we've just noted, can it explain mass. In order to give particles any mass at all, we have to introduce the notional Higgs boson. Whether it actually exists is a matter for 21st century physics. As Feynman cheerfully observed, so we are stuck with a theory, and we do not know whether it is right or wrong, but we do know that it is a little wrong, or at least incomplete. In an attempt to draw everything together, physicists have come up with something called superstring theory. This postulates that all those little things like quarks and leptons that we had previously thought of as particles are actually strings, vibrating strands of energy that oscillate in 11 dimensions, consisting of the 3 we know already, plus time, and 7 other dimensions that are, well, unknowable to us. The strings are very tiny, tiny enough to pass for point particles. By introducing extra dimensions, superstring theory enables physicists to pull together quantum laws and gravitational ones into one comparatively tidy package. But it also means that anything scientists say about the theory begins to sound worryingly like the sort of thoughts that would make you edge away if conveyed to you by a stranger on a park bench. Here, for example, is the physicist Michio Kaku explaining the structure of the universe from a superstring perspective. The heterotic string consists of a closed string that has 2 types of vibrations, clockwise and counterclockwise, which are treated differently. The clockwise vibrations live in a 10-dimensional space. The counterclockwise live in a 26-dimensional space, of which 16 dimensions have been compactified. We recall that in Kaluza's original 5-dimensional, the 5th dimension was compactified by being wrapped up into a circle. And so it goes, for some 350 pages. String theory has further spawned something called M-theory, which incorporates surfaces known as membranes, or simply brains, to the hipper souls of the world of physics. I'm afraid this is the stop on the knowledge highway where most of us must get off. Here is a sentence from the New York Times, explaining this as simply as possible to a general audience. The ekpyrotic process begins far in the indefinite past with a pair of flat, empty brains sitting parallel to each other in a warped 5-dimensional space. The 2 brains, which form the walls of the 5th dimension, could have popped out of nothingness as a quantum fluctuation in the even more distant past, and then drifted apart. No arguing with that. no understanding it either. Ekpyrotic, incidentally, comes from the Greek word for conflagration. Matters in physics have now reached such a pitch that, as Paul Davies noted in Nature, it is almost impossible for the non-scientist to discriminate between the legitimately weird and the outright crackpot. The question came, interestingly, to a head in the fall of 2002, when two French physicists, twin brothers Igor and Grigor Bogdanov, produced a theory of ambitious density involving such concepts as imaginary time and the Kubo-Schwinger-Martin condition, and purporting to describe the nothingness that was the universe before the Big Bang, a period that was always assumed to be unknowable, since it predated the birth of physics and its properties. Almost at once the Bogdanov paper excited debate among physicists as to whether it was twaddle, a work of genius, or a hoax. Scientifically, it's clearly more or less complete nonsense, Columbia University physicist Peter Woit told the New York Times. But these days that doesn't much distinguish it from a lot of the rest of the literature. Karl Popper, whom Steven Weinberg has called the Dean of Modern Philosophers of Science, once suggested that there may not be an ultimate theory for physics, that rather every explanation may require a further explanation, producing an infinite chain of more and more fundamental principles. A rival possibility is that such knowledge may simply be beyond us. So far, fortunately, writes Weinberg in Dreams of a Final Theory, we do not seem to be coming to the end of our intellectual resources. Almost certainly this is an area that will see further developments of thought, and almost certainly these thoughts will again be beyond most of us. While physicists in the middle decades of the 20th century were looking perplexedly into the world of the very small, astronomers were finding no less arresting an incompleteness of understanding in the universe at large. When we last met Edwin Hubble, he had determined that nearly all the galaxies in our field of view are flying away from us, and that the speed and distance of this retreat are neatly proportional. The farther away the galaxy, the faster it is moving. Hubble realized that this could be expressed with a simple equation. HO equals V over d, where HO is the constant, V is the recessional velocity of a flying galaxy, and d its distance away from us. HO has been known ever since as the Hubble constant, and the whole of Hubble's law. Using his formula, Hubble calculated that the universe was about 2 billion years old, which was a little awkward, because even by the late 1920s it was fairly obvious that many things within the universe, not least Earth itself, were probably older than that. Refining this figure has been an ongoing preoccupation of cosmology. Almost the only thing constant about the Hubble constant has been the amount of disagreement over what value to give it. In 1956, astronomers discovered that Cepheid variables were more variable than they had thought. They came in 2 varieties, not 1. This allowed them to rework their calculations and come up with a new age for the universe of from 7 to 20 billion years. Not terribly precise, but at least old enough at last to embrace the formation of the Earth. In the years that followed, there erupted a long-running dispute between Alan Sandage, heir to Hubble at Mount Wilson, and Gérard de Vaucouleurs, a French-born astronomer based at the University of Texas. Sandage, after years of careful calculations, arrived at a value for the Hubble constant of 50, giving the universe an age of 20 billion years. De Vaucouleurs was equally certain that the Hubble constant was 100. This would mean that the universe was only half the size and age that Sandage believed, 10 billion years. Matters took a further lurch into uncertainty when in 1994 a team from the Carnegie Observatories in California, using measures from the Hubble Space Telescope, suggested that the universe could be as little as 8 billion years old, an age even they conceded was younger than some of the stars within the universe. In February 2003, a team from NASA and the Goddard Space Flight Center in Maryland, using a new far-reaching type of satellite called the Wilkinson Microwave Anisotropy Probe, announced with some confidence that the age of the universe is 13.7 billion years, give or take 100 million years or so. There matters rest, at least for the moment. You are of course entitled to wonder what is meant exactly by a constant of 50, or a constant of 100. The answer lies in astronomical units of measure. Except conversationally, astronomers don't use light years. They use a distance called the parsec, a contraction of parallax and second, based on a universal measure called the stellar parallax, and equivalent to 3.26 light years. Really big measures, like the size of a universe, are measured in megaparsecs, a million parsecs. The constant is expressed in terms of kilometers per second per megaparsec. Thus, when astronomers refer to a Hubble constant of 50, what they really mean is 50 kilometers per second per megaparsec. For most of us, that is, of course, an utterly meaningless measure, but then with astronomical measures, most distances are so huge as to be utterly meaningless. The difficulty in making final determinations is that there are often acres of room for interpretation. Imagine standing in a field at night and trying to decide how far away two distant electric lights are. Using fairly straightforward tools of astronomy, you could easily enough determine that the bulbs are of equal brightness, and that one is, say, 50% more distant than the other. But what you can't be certain of is whether the nearer light is, let us say, a 58-watt bulb that is 122 feet away, or a 61-watt light that is 119 feet 8 inches away. On top of that, you must make allowances for distortions caused by variations in the Earth's atmosphere, by intergalactic dust contaminating light from foreground stars, and many other factors. The upshot is that your computations are necessarily based on a series of nested assumptions, any of which could be a source of contention. There is also the problem that access to telescopes is always at a premium, and historically measuring red shifts has been notably costly in telescope time. It could take all night to get a single exposure. In consequence, astronomers have sometimes been compelled, or willing, to base conclusions on notably scanty evidence. In cosmology, as the journalist Jeffrey Carr has suggested, we have a mountain of theory built on a molehill of evidence. Or as Martin Rees has put it, our present satisfaction with our state of understanding may reflect the paucity of the data rather than the excellence of the theory. This uncertainty applies, incidentally, to relatively nearby things as much as to the distant edges of the universe. As Donald Goldsmith notes, when astronomers say that the galaxy M87 is 60 million light-years away, what they really mean, but do not often stress to the general public, is that it is somewhere between 40 million and 90 million light-years away. Not quite the same thing. For the universe at large, matters are naturally magnified. Bearing all that in mind, the best bets these days for the age of the universe seem to be fixed on a range of about 12 billion to 13.5 billion years. But we remain a long way from unanimity. One interesting, recently suggested theory is that the universe is not nearly as big as we thought, that when we peer into the distance, some of the galaxies we see may simply be reflections, ghost images created by rebounded light. The fact is, there is a great deal, even at quite a fundamental level, that we don't know, not least what the universe is made of. When scientists calculate the amount of matter needed to hold things together, they always come up desperately short. It appears that at least 90% of the universe, and perhaps as much as 99%, is composed of Fritz Zwicky's dark matter, stuff that is by its nature invisible to us. It is slightly galling to think that we live in a universe that, for the most part, we can't even see. But there you are. At least the names for the two main possible culprits are entertaining. They are said to be either WIMPs, WIMPs, for weakly interacting massive particles, which is to say specks of invisible matter left over from a Big Bang, or MACHOs, machos, for massive compact halo objects, really just another name for black holes, brown dwarfs, and other very dim stars. Particle physicists have tended to favour the particle explanation of WIMPs, astrophysicists the stellar explanation of machos. For a time, machos had the upper hand, but not nearly enough of them were found, so sentiment swung back toward WIMPs, but with the problem that no WIMP has ever been found. Because they are weakly interacting, they are, assuming they even exist, very hard to detect. Cosmic rays would cause too much interference. So scientists must go deep underground. 1 kilometre underground, cosmic bombardments would be 1/1,000,000th what they would be on the surface. But even when all these are added in, 2/3 of the universe is still missing from the balance sheet, as one commentator has put it. For the moment, we might very well call them dunnos, for dark, unknown, non-reflective, non-detectable objects somewhere. Recent evidence suggests that not only are the galaxies of the universe racing away from us, but that they are doing so at a rate that is accelerating. This is counter to all expectations. It appears that the universe may not only be filled with dark matter, but with dark energy. Scientists sometimes also call it vacuum energy, or more exotically, quintessence. Whatever it is, it seems to be driving an expansion that no one can altogether account for. The theory is that empty space isn't so empty at all, that there are particles of matter and antimatter popping into existence and popping out again, and that these are pushing the universe outward at an accelerating rate. Improbably enough, the one thing that resolves all this is Einstein's cosmological constant, the little piece of math he dropped into the general theory of relativity to stop the universe's presumed expansion, and called the biggest blunder of my life. It now appears that he may have gotten things right after all. The upshot of all this is that we live in a universe whose age we can't quite compute, surrounded by stars whose distances we don't altogether know, filled with matter we can't identify, operating in conformance with physical laws whose properties we don't truly understand. And on that rather unsettling note, let's return to planet Earth and consider something that we do understand, though by now you perhaps won't be surprised to hear that we don't understand it completely, and what we do understand we haven't understood for long. 12. The Earth moves. In one of his last professional acts before his death in 1955, Albert Einstein wrote a short but glowing foreword to a book by a geologist named Charles Hapgood entitled Earth's Shifting Crust, a key to some basic problems of Earth science. Hapgood's book was a steady demolition of the idea that continents were in motion. In a tone that all but invited the reader to join him in a tolerant chuckle, Hapgood observed that a few gullible souls had noticed an apparent correspondence in shape between certain continents. It would appear, he went on, that South America might be fitted together with Africa, and so on. It is even claimed that rock formations on opposite sides of the Atlantic match. Mr. Hapgood briskly dismissed any such notions, noting that the geologists K.E. Castor and J.C. Mendes had done extensive fieldwork on both sides of the Atlantic and had established beyond question that no such similarities existed. Goodness knows what outcrops Messrs. Castor and Mendes had looked at, because in fact many of the rock formations on both sides of the Atlantic are the same, not just very similar, but the same. This was not an idea that flew with Mr. Hapgood or many other geologists of his day. The theory Hapgood alluded to was one first propounded in 1908 by an amateur American geologist named Frank Bursley Taylor. Taylor came from a wealthy family and had both the means and freedom from academic constraints to pursue unconventional lines of inquiry. He was one of those struck by the similarity in shape between the facing coastlines of Africa and South America. But from this observation he developed the idea that the continents had once slid around. He suggested, presciently as it turned out, that the crunching together of continents could have thrust up the world's mountain chains. He failed, however, to produce much in the way of evidence, and the theory was considered too crackpot to merit serious attention. In Germany, however, Taylor's idea was picked up, and effectively appropriated by a theorist named Alfred Wegener, a meteorologist at the University of Marburg. Wegener investigated the many plant and fossil anomalies that did not fit comfortably into the standard model of Earth history, and realized that very little of it made sense if conventionally interpreted. Animal fossils repeatedly turned up on opposite sides of oceans that were clearly too wide to swim. How, he wondered, did marsupials travel from South America to Australia? How did identical snails turn up in Scandinavia and New England? And how, come to that, did one account for coal seams and other semi-tropical remnants in frigid spots like Spitsbergen, 400 miles north of Norway, if they had not somehow migrated there from warmer climes? Wegener developed the theory that the world's continents had once come together in a single landmass he called Pangaea, where flora and fauna had been able to mingle before the continents had split apart and floated off to their present positions. All this he put together in a book called Die Entstehung der Kontinente und Ozeane, or The Origin of Continents and Oceans, which was published in German in 1912, and, despite the outbreak of the First World War in the meantime, in English 3 years later. Because of the war, Wegener's theory didn't attract much notice at first, but by 1920, when he produced a revised and expanded edition, it quickly became a subject of discussion. Everyone agreed that continents moved, but up and down, not sideways. The process of vertical movement, known as isostasy, was a foundation of geological beliefs for generations, though no one had any good theories as to how or why it happened. One idea, which remained in textbooks well into my own school days, was the baked apple theory propounded by the Austrian Edward Suess just before the turn of the century. This suggested that as the molten earth had cooled, it had become wrinkled in the manner of a baked apple, creating ocean basins and mountain ranges. Never mind that James Hutton had shown long before that any such static arrangement would eventually result in a featureless spheroid as erosion levelled the bumps and filled in the divots. There was also the problem, demonstrated by Rutherford and Soddy early in the century, that earthly elements hold huge reserves of heat, much too much to allow for the sort of cooling and shrinking Suess suggested. And anyway, if Suess's theory was correct, then mountains should be evenly distributed across the face of the earth, which patently they were not, and of more or less the same ages. Yet by the early 1900s it was already evident that some ranges, like the Urals and Appalachians, were hundreds of millions of years older than others, like the Alps and Rockies. Clearly the time was ripe for a new theory. Unfortunately, Alfred Wegener was not the man that geologists wished to provide it. For a start, his radical notions questioned the foundations of their discipline, seldom an effective way to generate warmth in an audience. Such a challenge would have been painful enough coming from a geologist, but Wegener had no background in geology. He was a meteorologist, for goodness sake. A weatherman, a German weatherman. These were not remediable deficiencies. And so geologists took every pain they could think of to dismiss his evidence and belittle his suggestions. To get around the problems of fossil distributions, they posited ancient land bridges wherever they were needed. When an ancient horse named Hipparion was found to have lived in France and Florida at the same time, a land bridge was drawn across the Atlantic. When it was realized that ancient tapirs had existed simultaneously in South America and Southeast Asia, a land bridge was drawn there, too. Soon, maps of prehistoric seas were almost solid with hypothesized land bridges from North America to Europe, from Brazil to Africa, from Southeast Asia to Australia, from Australia to Antarctica. These connective tendrils had not only conveniently appeared whenever it was necessary to move a living organism from one landmass to another, but then obligingly vanished without leaving a trace of their former existence. None of this, of course, was supported by so much as a grain of actual evidence. Nothing so wrong could be. Yet it was geological orthodoxy for the next half-century. Even land bridges couldn't explain some things. One species of trilobite that was well known in Europe was also found to have lived on Newfoundland, but only on one side. No one could persuasively explain how it had managed to cross 2,000 miles of hostile ocean, but then failed to find its way around the corner of a 200-mile-wide island. Even more awkwardly anomalous was another species of trilobite found in Europe and the Pacific Northwest, but nowhere in between, which would have required not so much a land bridge as a flyover. Yet as late as 1964, when the Encyclopaedia Britannica discussed the rival theories, it was Wegener's that was held to be full of numerous grave theoretical difficulties. To be sure, Wegener made mistakes. He asserted that Greenland is drifting west by about a mile a year, which is clearly nonsense. It's more like half an inch. Above all, he could offer no convincing explanation for how the land masses moved about. To believe in his theory, you had to accept that massive continents somehow pushed through solid crust like a plough through soil, without leaving any furrow in their wake. Nothing then known could plausibly explain what motored these massive movements. It was Arthur Holmes, the English geologist who did so much to determine the age of the Earth, who suggested a possible way. Holmes was the first scientist to understand that radioactive warming could produce convection currents within the Earth. In theory, these could be powerful enough to slide continents around on the surface. In his popular and influential textbook, Principles of Physical Geology, first published in 1944, Holmes laid out a continental drift theory that was in its fundamentals the theory that prevails today. It was still a radical proposition for the time and widely criticized, particularly in the United States, where resistance to drift lasted longer than elsewhere. One reviewer there fretted, without any evident sense of irony, that Holmes presented his arguments so clearly and compellingly that students might actually come to believe them. Elsewhere, however, the new theory drew steady, if cautious, support. In 1950, a vote at the annual meeting of the British Association for the Advancement of Science showed that about half of those present now embraced the idea of continental drift. Hapgood soon after cited this figure as proof of how tragically misled British geologists had become. Curiously, Holmes himself sometimes wavered in his conviction. In 1953 he confessed, "I have never succeeded in freeing myself from a nagging prejudice against continental drift. In my geological bones, so to speak, I feel the hypothesis is a fantastic one." Continental drift was not entirely without support in the United States. Reginald Daly of Harvard spoke for it, but he, you may recall, was the man who suggested that the moon had been formed by a cosmic impact, and his ideas tended to be considered interesting, even worthy, but a touch too exuberant for serious consideration. And so most American academics stuck to the theory that the continents had occupied their present positions forever, and that their surface features could be attributed to something other than lateral motions. Interestingly, oil company geologists had known for years that if you wanted to find oil, you had to allow for precisely the sort of surface movements that were implied by plate tectonics. But oil geologists didn't write academic papers, they just found oil. There was one other major problem with Earth theories that no one had resolved, or even come close to resolving. That was the question of where all the sediments went. Every year, Earth's rivers carried massive volumes of eroded material, 500 million tons of calcium, for instance, to the seas. If you multiply the rate of deposition by the number of years it had been going on, it produced a disturbing figure. There should be about 12 miles of sediments on the ocean bottoms. Or, put another way, the ocean bottoms should by now be well above the ocean tops. Scientists dealt with this paradox in the handiest possible way. They ignored it. But eventually there came a point when they could ignore it no longer. In the Second World War, a Princeton University mineralogist named Harry Hess was put in charge of an attack transport ship, the USS Cape Johnson. Aboard this vessel was a fancy new depth sounder called a fathometer, which was designed to facilitate inshore maneuvers during beach landings. But Hess realized that it could equally well be used for scientific purposes, and never switched it off, even when far out at sea, even in the heat of battle. What he found was entirely unexpected. If the ocean floors were ancient, as everyone assumed, they should be thickly blanketed with sediments, like the mud on the bottom of a river or lake. But Hess's readings showed that the ocean floor offered anything but the gooey smoothness of ancient silts. It was scored everywhere with canyons, trenches, and crevasses, and dotted with volcanic seamounts that he called geos, after an earlier Princeton geologist named Arnold Guyot. All this was a puzzle. But Hess had a war to take part in, and put such thoughts to the back of his mind. After the war, Hess returned to Princeton and the preoccupations of teaching, but the mysteries of the sea floor continued to occupy a space in his thoughts. Meanwhile, throughout the 1950s, oceanographers were undertaking more and more sophisticated surveys of the ocean floors. In so doing, they found an even bigger surprise. The mightiest and most extensive mountain range on Earth was, mostly, underwater. It traced a continuous path along the world's seabeds, rather like the stitching on a baseball. If you began at Iceland, you could follow it down the center of the Atlantic Ocean, around the bottom of Africa, and across the Indian and Southern Oceans, below Australia. There it angled across the Pacific as if making for Baja California before shooting up the west coast of the United States to Alaska. Occasionally its higher peaks poked above the water as an island or archipelago, the Azores or Canaries in the Atlantic, Hawaii in the Pacific, for instance. But mostly it was buried under thousands of fathoms of salty sea, unknown and unsuspected. When all its branches were added together, the network extended to 46,600 miles. A very little of this had been known for some time. People laying ocean floor cables in the 19th century had realized that there was some kind of mountainous intrusion in the mid-Atlantic from the way the cables ran, but the continuous nature and overall scale of the chain was a stunning surprise. Moreover, it contained physical anomalies that couldn't be explained. Down the middle of the mid-Atlantic ridge was a canyon, a rift up to a dozen miles wide for its entire 12,000-mile length. This seemed to suggest that the Earth was splitting apart at the seams, like a nut bursting out of its shell. It was an absurd and unnerving notion, but the evidence couldn't be denied. Then in 1960, core samples showed that the ocean floor was quite young at the mid-Atlantic ridge, but grew progressively older as you moved away from it to the east or west. Harry Hess considered the matter, and realized that this could mean only one thing. New ocean crust was being formed on either side of the central rift, then being pushed away from it as new crust came along behind. The Atlantic floor was effectively two large conveyor belts, one carrying crust toward North America, the other carrying crust toward Europe. The process became known as seafloor spreading. When the crust reached the end of its journey at the boundary with continents, it plunged back into the earth in a process known as subduction. That explained where all the sediment went. It was being returned to the bowels of the earth. It also explained why ocean floors everywhere were so comparatively youthful. None had ever been found to be older than about 175 million years, which was a puzzle because continental rocks were often billions of years old. Now Hess could see why. Ocean rocks lasted only as long as it took them to travel to shore. It was a beautiful theory that explained a great deal. Hess elaborated his ideas in an important paper, which was almost universally ignored. Sometimes the world just isn't ready for a good idea. Meanwhile, two researchers working independently were making some startling findings by drawing on a curious fact of Earth history that had been discovered several decades earlier. In 1906, a French physicist named Bernard Brune had found that the planet's magnetic field reverses itself from time to time, and that the record of these reversals is permanently fixed in certain rocks at the time of their birth. Specifically, tiny grains of iron ore within the rocks point to where the magnetic poles happen to be at the time of their formation, then stay pointing in that direction as the rocks cool and harden. In effect, they remember where the magnetic poles were at the time of their creation. For years this was little more than a curiosity, but in the 1950s Patrick Blackett of the University of London and S.K. Runcorn of the University of Newcastle studied the ancient magnetic patterns frozen in British rocks, and were startled, to say the very least, to find them indicating that at some time in the distant past Britain had spun on its axis and travelled some distance to the north, as if it had somehow come loose from its moorings. Moreover, they also discovered that if you placed a map of Europe's magnetic patterns alongside an American one from the same period, they fit together as neatly as two halves of a torn letter. It was uncanny. Their findings were ignored too. It finally fell to two men from Cambridge University, a geophysicist named Drummond Matthews and a graduate student of his named Fred Vine, to draw all the strands together. In 1963, using magnetic studies of the Atlantic Ocean floor, they demonstrated conclusively that the sea floors were spreading in precisely the manner Hess had suggested, and that the continents were in motion too. An unlucky Canadian geologist named Lawrence Morley came up with the same conclusion at the same time, but couldn't find anyone to publish his paper. In what has become a famous snub, the editor of the Journal of Geophysical Research told him, "Such speculations make interesting talk at cocktail parties, but it is not the sort of thing that ought to be published under serious scientific aegis." One geologist later described it as probably the most significant paper in the earth sciences ever to be denied publication. At all events, mobile crust was an idea whose time had finally come. A symposium of many of the most important figures in the field was convened in London under the auspices of the Royal Society in 1964, and suddenly, it seemed, everyone was a convert. The Earth, the meeting agreed, was a mosaic of interconnected segments whose various stately jostlings accounted for much of the planet's surface behavior. The name continental drift was fairly swiftly discarded when it was realized that the whole crust was in motion and not just the continents. But it took a while to settle on a name for the individual segments. At first, people called them crustal blocks, or sometimes paving stones. Not until late 1968, with the publication of an article by 3 American seismologists in the Journal of Geophysical Research, did the segments receive the name by which they have since been known: plates. The same article called the new science plate tectonics. Old ideas die hard, and not everyone rushed to embrace the exciting new theory. Well into the 1970s, one of the most popular and influential geological textbooks, The Earth, by the venerable Harold Jeffreys, strenuously insisted that plate tectonics was a physical impossibility, just as it had in the first edition way back in 1924. It was equally dismissive of convection and sea floor spreading, and in Basin and Range, published in 1980, John McPhee noted that even then 1 American geologist in 8 still didn't believe in plate tectonics. Today we know that Earth's surface is made up of 8 to 12 big plates, depending on how you define big, and 20 or so smaller ones, and they all move in different directions and at different speeds. Some plates are large and comparatively inactive, others small but energetic. They bear only an incidental relationship to the land masses that sit upon them. The North American plate, for instance, is much larger than the continent with which it is associated. It roughly traces the outline of the continent's west coast, which is why that area is so seismically active because of the bump and crush of the plate boundary, but ignores the eastern seaboard altogether and instead extends halfway across the Atlantic to the mid-ocean ridge. Iceland is split down the middle, which makes it tectonically half American and half European. New Zealand, meanwhile, is part of the immense Indian Ocean plate, even though it is nowhere near the Indian Ocean. And so it goes for most plates. The connections between modern land masses and those of the past were found to be infinitely more complex than anyone had imagined. Kazakhstan, it turns out, was once attached to Norway and New England. One corner of Staten Island, but only a corner, is European. So is part of Newfoundland. Pick up a pebble from a Massachusetts beach, and its nearest kin will now be in Africa. The Scottish Highlands and much of Scandinavia are substantially American. Some of the Shackleton Range of Antarctica, it is thought, may have once belonged to the Appalachians of the eastern U.S. Rocks, in short, get around. The constant turmoil keeps the plates from fusing into a single immobile plate. Assuming things continue much as at present, the Atlantic Ocean will expand until eventually it is much bigger than the Pacific. Much of California will float off and become a kind of Madagascar of the Pacific. Africa will push northward into Europe, squeezing the Mediterranean out of existence and thrusting up a chain of mountains of Himalayan majesty running from Paris to Calcutta. Australia will colonize the islands to its north and connect by some isthmian umbilicus to Asia. These are future outcomes, but not future events. The events are happening now. As we sit here, continents are adrift like leaves on a pond. Thanks to global positioning systems, we can see that Europe and North America are parting at about the speed a fingernail grows, roughly 2 yards in a human lifetime. If you were prepared to wait long enough, you could ride from Los Angeles all the way up to San Francisco. It is only the brevity of lifetimes that keeps us from appreciating the changes. Look at a globe, and what you are seeing really is a snapshot of the continents as they have been for just 0.1% of the Earth's history. Earth is alone among the rocky planets in having tectonics, and why this should be is a bit of a mystery. It is not simply a matter of size or density. Venus is nearly a twin of Earth in these respects, and yet has no tectonic activity. It is thought, though it is really nothing more than a thought, that tectonics is an important part of the planet's organic well-being. As the physicist and writer James Trefil has put it would be hard to believe that the continuous movement of tectonic plates has no effect on the development of life on Earth. He suggests that the challenges induced by tectonics, changes in climate for instance, were an important spur to the development of intelligence. Others believe the driftings of the continents may have produced at least some of the Earth's various extinction events. In November of 2002, Tony Dixon of Cambridge University in England produced a report published in the journal Science, strongly suggesting that there may well be a relationship between the history of rocks and the history of life. What Dixon established was that the chemical composition of the world's oceans has altered abruptly and vigorously throughout the past 500 million years, and that these changes often correlate with important events in biological history. The huge outburst of tiny organisms that created the chalk cliffs of England's south coast, the sudden fashion for shells among marine organisms during the Cambrian period, and so on. No one can say what causes the ocean's chemistry to change so dramatically from time to time, but the opening and shutting of ocean ridges would be an obvious possible culprit. At all events, plate tectonics not only explained the surface dynamics of the Earth, how an ancient Hipparion got from France to Florida, for example, but also many of its internal actions. Earthquakes, the formation of island chains, the carbon cycle, the locations of mountains, the coming of ice ages, the origins of life itself, there was hardly a matter that wasn't directly influenced by this remarkable new theory. Geologists, as McPhee has noted, found themselves in the giddying position that the whole Earth suddenly made sense. But only up to a point. The distribution of continents in former times is much less neatly resolved than most people outside geophysics think. Although textbooks give confident-looking representations of ancient land masses with names like Laurasia, Gondwana, Rodinia, and Pangaea, these are sometimes based on conclusions that don't altogether hold up. As George Gaylord Simpson observes in Fossils and the History of Life, species of plants and animals from the ancient world have a habit of appearing inconveniently where they shouldn't, and failing to be where they ought. The outline of Gondwana, a once mighty continent connecting Australia, Africa, Antarctica, and South America, was based in large part on the distribution of a genus of ancient tongue fern called Glossopteris, which was found in all the right places. However, much later, Glossopteris was also discovered in parts of the world that had no known connection to Gondwana. This troubling discrepancy was, and continues to be, mostly ignored. Similarly, a Triassic reptile called Lystrosaurus has been found from Antarctica all the way to Asia, supporting the idea of a former connection between those continents, but it has never turned up in South America or Australia, which are believed to have been part of the same continent at the same time. There are also many surface features that tectonics can't explain. Take Denver. It is, as everyone knows, a mile high, but that rise is comparatively recent. When dinosaurs roamed the Earth, Denver was part of an ocean bottom, many thousands of feet lower. Yet the rocks on which Denver sits are not fractured or deformed in the way they would be if Denver had been pushed up by colliding plates, and anyway, Denver was too far from the plate edges to be susceptible to their actions. It would be as if you pushed against the edge of a rug, hoping to raise a ruck at the opposite end. Mysteriously, and over millions of years, it appears that Denver has been rising, like baking bread. So too has much of southern Africa. A portion of it, 1,000 miles across, has risen nearly a mile in 100 million years, without any known associated tectonic activity. Australia, meanwhile, has been tilting and sinking. Over the past 100 million years, as it has drifted north toward Asia, its leading edge has sunk by some 600 feet. It appears that Indonesia is very slowly drowning and dragging Australia down with it. Nothing in the theories of tectonics can explain any of this. Alfred Wegener never lived to see his ideas vindicated. On an expedition to Greenland in 1930, he set out alone on his 50th birthday to check out a supply drop. He never returned. He was found a few days later frozen to death on the ice. He was buried on the spot and lies there yet, but about a yard closer to North America than on the day he died. Einstein also failed to live long enough to see that he had backed the wrong horse. In fact, he died at Princeton, New Jersey in 1955, before Charles Hapgood's rubbishing of continental drift theories was even published. The other principal player in the emergence of tectonics theory, Harry Hess, was also at Princeton at the time and would spend the rest of his career there. One of his students was a bright young fellow named Walter Alvarez, who would eventually change the world of science in a quite different way. As for geology itself, its cataclysms had only just begun, and it was young Alvarez who helped to start the process. Part 4. Dangerous Planet. The history of any one part of the Earth, like the life of a soldier, consists of long periods of boredom and short periods of terror. British geologist Derek V. Ager. 13. Bang. People knew for a long time that there was something odd about the earth beneath Manson, Iowa. In 1912, a man drilling a well for the town water supply reported bringing up a lot of strangely deformed rock, crystalline clast breccia with a melt matrix and overturned ejector flap, as it was later described in an official report. The water was odd too. It was almost as soft as rainwater. Naturally occurring soft water had never been found in Iowa before. Though Manson's strange rocks and silken waters were matters of curiosity, 41 years would pass before a team from the University of Iowa got around to making a trip to the community. Then, as now, a town of about 2,000 people in the northwest part of the state. In 1953, after sinking a series of experimental bores, university geologists agreed that the site was indeed anomalous, and attributed the deformed rocks to some ancient, unspecified volcanic action. This was in keeping with the wisdom of the day, but it was also about as wrong as a geological conclusion can get. The trauma to Manson's geology had come not from within the Earth, but from at least 100 million miles beyond. Sometime in the very ancient past, when Manson stood on the edge of a shallow sea, a rock about 1.5 miles across, weighing 10 billion tons, and travelling at perhaps 200 times the speed of sound, ripped through the atmosphere and punched into the earth with a violence and suddenness that we can scarcely imagine. Where Manson now stands became in an instant a hole 3 miles deep and more than 20 miles across. The limestone that elsewhere gives Iowa its hard, mineralized water was obliterated and replaced by the shocked basement rocks that so puzzled the water driller in 1912. The Manson impact was the biggest thing that has ever occurred on the mainland United States, of any type, ever. The crater it left behind was so colossal that if you stood on one edge, you would only just be able to see the other side on a good day. It would make the Grand Canyon look quaint and trifling. Unfortunately for lovers of spectacle, 2.5 million years of passing ice sheets filled the Manson crater right to the top with rich glacial till, then graded it smooth, so that today the landscape at Manson and for miles around is as flat as a tabletop, which is of course why no one has ever heard of the Manson crater. At the library in Manson they are delighted to show you a collection of newspaper articles and a box of core samples from a 1991-92 drilling program. Indeed, they positively bustle to produce them. but you have to ask to see them. Nothing permanent is on display, and nowhere in the town is there any historical marker. To most people in Manson, the biggest thing ever to happen was a tornado that rolled up Main Street in 1979, tearing apart the business district. One of the advantages of all that surrounding flatness is that you can see danger from a long way off. Virtually the whole town turned out at one end of Main Street and watched for half an hour as the tornado came toward them, hoping it would veer off, then prudently scampered when it did not. 4 of them, alas, didn't move quite fast enough and were killed. Every June now, Manson has a week-long event called Crater Days, which was dreamed up as a way of helping people forget that unhappy anniversary. It doesn't really have anything to do with the crater. Nobody's figured out a way to capitalize on an impact site that isn't visible. Very occasionally we get people coming in and asking where they should go to see the crater, and we have to tell them that there is nothing to see, says Anna Schlapkohl, the town's friendly librarian. Then they go away kind of disappointed. However, most people, including most Iowans, have never heard of the Manson crater. Even for geologists, it barely rates a footnote. But for one brief period in the 1980s, Manson was the most geologically exciting place on Earth. The story begins in the early 1950s, when a bright young geologist named Eugene Shoemaker paid a visit to Meteor Crater in Arizona. Today, Meteor Crater is the most famous impact site on Earth and a popular tourist attraction. In those days, however, it didn't receive many visitors and was still often referred to as Barringer Crater, after a wealthy mining engineer named Daniel M. Barringer, who had staked a claim on it in 1903. Barringer believed that the crater had been formed by a 10-million-ton meteor, heavily freighted with iron and nickel, and it was his confident expectation that he would make a fortune digging it out. Unaware that the meteor and everything in it would have been vaporized on impact, he wasted a fortune, and the next 26 years cutting tunnels that yielded nothing. By the standards of today, crater research in the early 1900s was a trifle unsophisticated, to say the least. The leading early investigator, G.K. Gilbert of Columbia University, modeled the effects of impacts by flinging marbles into pans of oatmeal. For reasons I cannot supply, Gilbert conducted these experiments not in a laboratory at Columbia, but in a hotel room. Somehow, from this, Gilbert concluded that the moon's craters were indeed formed by impacts, in itself quite a radical notion for the time, but that the Earth's were not. Most scientists refuse to go even that far. To them, the moon's craters were evidence of ancient volcanoes, and nothing more. The few craters that remained evident on Earth, most had been eroded away, were generally attributed to other causes or treated as fluky rarities. By the time Shoemaker came along, a common view was that Meteor Crater had been formed by an underground steam explosion. Shoemaker knew nothing about underground steam explosions. He couldn't. They don't exist. But he did know all about blast zones. One of his first jobs out of college was to study explosion rings at the Yucca Flats nuclear test site in Nevada. He concluded, as Barringer had before him, that there was nothing at Meteor Crater to suggest volcanic activity, but that there were huge distributions of other stuff, anomalous fine silicas and magnetites principally, that suggested an impact from space. Intrigued, he began to study the subject in his spare time. Working first with his colleague Eleanor Helen and later with his wife Carolyn and associate David Levy, Shoemaker began a systematic survey of the inner solar system. They spent 1 week each month at the Palomar Observatory in California looking for objects, asteroids primarily, whose trajectories carried them across Earth's orbit. At the time we started, only slightly more than a dozen of these things had ever been discovered in the entire course of astronomical observation, Shoemaker recalled some years later in a television interview. Astronomers in the 20th century essentially abandoned the solar system, he added. Their attention was turned to the stars, the galaxies. What Shoemaker and his colleagues found was that there was more risk out there, a great deal more, than anyone had ever imagined. Asteroids, as most people know, are rocky objects orbiting in loose formation in a belt between Mars and Jupiter. In illustrations they are always shown as existing in a jumble, But in fact, the solar system is quite a roomy place, and the average asteroid actually will be about 1 million miles from its nearest neighbour. Nobody knows even approximately how many asteroids there are tumbling through space, but the number is thought to be probably not less than 1 billion. They are presumed to be planets that never quite made it, owing to the unsettling gravitational pull of Jupiter, which kept and keeps them from coalescing. When asteroids were first detected in the 1800s, the very first was discovered on the first day of the century by a Sicilian named Giuseppe Piazzi, they were thought to be planets, and the first two were named Ceres and Pallas. It took some inspired deductions by the astronomer William Herschel to work out that they were nowhere near planet-sized, but much smaller. He called them asteroids, Latin for star-like, which was slightly unfortunate, as they are not like stars at all. Sometimes now they are more accurately called planetoids. Finding asteroids became a popular activity in the 1800s, and by the end of the century about 1,000 were known. The problem was that no one was systematically recording them. By the early 1900s, it had often become impossible to know whether an asteroid that popped into view was new, or simply one that had been noted earlier and then lost track of. By this time, too, astrophysics had moved on so much that few astronomers wanted to devote their lives to anything as mundane as rocky planetoids. Only a few astronomers, notably Gerard Kuiper, the Dutch-born astronomer for whom the Kuiper belt of comets is named, took any interest in the solar system at all. Thanks to his work at the McDonald Observatory in Texas, followed later by work done by others at the Minor Planet Center in Cincinnati and the Spacewatch project in Arizona, a long line of lost asteroids was gradually whittled down until by the close of the 20th century only one known asteroid was unaccounted for, an object called 719 Albert. Last seen in October 1911, it was finally tracked down in 2000 after being missing for 89 years. So, from the point of view of asteroid research, the 20th century was essentially just a long exercise in bookkeeping. It is really only in the last few years that astronomers have begun to count and keep an eye on the rest of the asteroid community. As of July 2001, 26,000 asteroids had been named and identified, half in just the previous 2 years. With up to 1 billion to identify, the count obviously has barely begun. In a sense, it hardly matters. Identifying an asteroid doesn't make it safe. Even if every asteroid in the solar system had a name and known orbit, no one could say what perturbations might send any of them hurtling toward us. We can't forecast rock disturbances on our own surface, put them adrift in space, and what they might do is beyond guessing. Any asteroid out there that has our name on it is very likely to have no other. Think of the Earth's orbit as a kind of freeway on which we are the only vehicle, but which is crossed regularly by pedestrians who don't know enough to look before stepping off the curb. At least 90% of these pedestrians are quite unknown to us. We don't know where they live, what sort of hours they keep, how often they come our way. All we know is that at some point, at certain intervals, they trundle across the road down which we are cruising at 66,000 miles an hour. As Stephen Ostro of the Jet Propulsion Laboratory has put it, suppose that there was a button you could push, and you could light up all the Earth-crossing asteroids larger than about 10 meters. There would be over 100 million of these objects in the sky. In short, you would see not a couple of thousand distant twinkling stars, but millions upon millions upon millions of nearer, randomly moving objects, all of which are capable of colliding with the Earth, and all of which are moving on slightly different courses through the sky at different rates. It would be deeply unnerving. Well, be unnerved, because it is there. We just can't see it. Altogether it is thought, though it is really only a guess based on extrapolating from cratering rates on the Moon, that some 2,000 asteroids big enough to imperil civilized existence regularly cross our orbit. But even a small asteroid, the size of a house, say, could destroy a city. The number of these relative tiddlers in Earth-crossing orbits is almost certainly in the hundreds of thousands and possibly in the millions, and they are nearly impossible to track. The first one wasn't spotted until 1991, and that was after it had already gone by. Named 1991 BA, it was noticed as it sailed past us at a distance of 106,000 miles. in cosmic terms the equivalent of a bullet passing through one's sleeve without touching the arm. 2 years later, another, somewhat larger asteroid missed us by just 90,000 miles, the closest pass yet recorded. It, too, was not seen until it had passed, and would have arrived without warning. According to Timothy Ferris, writing in The New Yorker, such near misses probably happen 2 or 3 times a week and go unnoticed. An object 100 yards across couldn't be picked up by any Earth-based telescope until it was within just a few days of us, and that is only if your telescope happened to be trained on it, which is unlikely because even now the number of people searching for such objects is modest. The arresting analogy that is always made is that the number of people in the world who are actively searching for asteroids is fewer than the staff of a typical McDonald's restaurant. It is actually somewhat higher now, but not much. While Gene Shoemaker was trying to get people galvanized about the potential dangers of the inner solar system, another development, wholly unrelated on the face of it, was quietly unfolding in Italy, with the work of a young geologist from the Lamont Doherty Laboratory at Columbia University. In the early 1970s, Walter Alvarez was doing fieldwork in a comely defile known as the Bottaccione Gorge, near the Umbrian hill town of Gubbio, when he grew curious about a thin band of reddish clay that divided 2 ancient layers of limestone, one from the Cretaceous period, the other from the Tertiary. This is a point known to geology as the KT boundary, and it marks the time, 65 million years ago, when the dinosaurs and roughly half the world's other species of animals abruptly vanished from the fossil record. It is KT rather than CT, because C had already been appropriated for Cambrian. Depending on which source you credit, the K comes either from the Greek Krita or German Kreide. Both conveniently mean chalk, which is also what Cretaceous means. Alvarez wondered what it was about a thin lamina of clay, barely 1/4 of an inch thick, that could account for such a dramatic moment in Earth's history. At the time, the conventional wisdom about the dinosaur extinction was the same as it had been in Charles Lyell's day a century earlier, namely that the dinosaurs had died out over millions of years. But the thinness of the clay layer clearly suggested that in Umbria, if nowhere else, something rather more abrupt had happened. Unfortunately, in the 1970s, no tests existed for determining how long such a deposit might have taken to accumulate. In the normal course of things, Alvarez almost certainly would have had to leave the problem at that. But luckily he had an impeccable connection to someone outside his discipline who could help, his father, Luis. Luis Alvarez was an eminent nuclear physicist. He had won the Nobel Prize for Physics the previous decade. He had always been mildly scornful of his son's attachment to rocks, but this problem intrigued him. It occurred to him that the answer might lie in dust from space. Every year, the Earth accumulates some 30,000 metric tons of cosmic ferules, space dust in plainer language, which would be quite a lot if you swept it into one pile, but it is infinitesimal when spread across the globe.
This book is continued on Disc 7.